should have started. All right. So the neural network lab. So what are we going to build? Well, we're going to build, like I said, a very, very basic network. So we are essentially going to build the original Macaulay-Pitts network. Well, a little bit better. So Rosenblatt's perceptron. We're essentially going to build a perceptron. And we're going to see if a single one-layer network can build the XOR gate, right? And if it fails, if it fails in building the XOR gate, then how exactly does it fail? Right? Like which values does it successfully tolerate and which values does it not tolerate? And then we'll see if that if that simple this simple two-layer two-unit network does it also is it able to handle an AND gate, right, or an OR gate, right? So that's essentially what we need to know. The XOR or the XOR gate is, as you know, only gives you a high value if the inputs are different. If the inputs are same, you get a low value. That's all there is to it, right? And we will put in a few different activation functions, but we're not going to do much more than that. We're essentially just going to do these calculations, and we're going to see how, if we are training these parameters, how fast can we get something that has a low enough loss value, right? And we are going to see the difference between a loss value and being accurate, right? So a loss value is, let's say for your XOR, for your XOR, if your output has to be 1, but you get a value of 0.7, then your loss is 0.3, right? And if you are getting a value of 0.49, then your loss is 0.51. But your accuracy is when you round that value up. So a 0.49 would round to 0, and a 0.7 would round to 1. Right? So you can see that your accuracy is going to be 50%, while your loss is going to be somewhere around 0.6. So we're going to see the difference between them. As usual, let me open the terminal. So as usual, I'm going to just search code. Right. So I'm just going to use Jupyter Lab. And we're not going to do anything too complicated, so that should be fine. So let's bring that up. Okay. Let me bring up the screen. Where is it? Okay, there it is. Okay. Oh. So the problem with having multiple screens is that sometimes it gets kind of complicated. Where is? Okay, there's the Jupyter. All right, let's full screen. Let's zoom in a little bit so that you can see. Okay. So we are doing a little bit of matrix math, so we are going to need NumPy. So let's import NumPy as NP, just in case. Let's make sure everything is fine. Okay, so what are we doing? Okay, so we are building this, right? We're building this network, right? And the way we are building this network is essentially we are constructing this neuron, right? So each output value, the output value that you see here, is the weighted sum of these inputs, right? So all of these outputs, the output of H3 and H4, is W13 times I1, W23 times I2 minus some threshold value, right? So these weights, the job of these weights, all of these W13, W14, like we talked about yesterday, is essentially to determine how important any of these inputs are, how important any of these previous inputs are. right? And plus that threshold value that we talked about, right? So this threshold or bias or whatever you want to call it, the bias, all the bias does is it shifts the point of decision, right? Like it figures out the point where the output goes from high to low, right? The decision boundary, so to speak. Right? So let's the first thing we should do is define like this neuron. So let's define this particular neuron, right? So which is very simple, right? So let's define an individual single neuron, right? So uh, what are the inputs? As you saw here, uh, so for a single neuron, you have two inputs, x1, x2, I1, I2, whatever, and two weights and a bias. Right? So you have x1, x2, a weight. Let's give it a default value of 0.1, I think was what we were giving to most of them. Yeah, I think 0.1 was the default weight that we were giving. So let's give it 0.1, another weight of 0.1. Uh, what else? The threshold, right? So the threshold or the bias or whatever you call it. So like let's give it a T. Initially, let's not give it any threshold at all. So let's assign it a 0, right? So that's these are the default values. So what is the output? The output is the weighted sum of all of them plus the bias, right? So it's very simple, right? So this is not even matrix one. So this is W1 times X1 plus W2 times X2 plus the bias, the threshold. So this is the weighted sum. And then the output is determined by the activation function, right? Okay, let me rename this to now an activation function decides whether this neuron is going to be activated or not. Let's not make it very complicated. Let's just put in a very simple step function because that was the first function that we saw. Right, this sign function or the step function is the most basic function, which is this, which is essentially a clamp. So let's put in a clamp. So the output is going to be a clamp, right? So it's going to be uh, 1 if high or 0 if low. So 1 if this output, if z is greater than 0, then it's high, otherwise it's 0. And then you return z and you return the output.
Professor, you misspelled W2.
Oh, right. Thank you. Thank you so much. Right. That's it. So let's take a look at the result. So what is the output of like 1 0 0 0 1 1? So that's let's see. So print for 1 comma 0. Oops. I'm still in the habit of Python 2.0, where you didn't need brackets to call the print function. Right? So that's unfortunate. Well, what do you need? So we need to convert to string. We need single neuron. Uh, yeah. Let's give it an input of 1 comma 0. And what we first want is the z value. So 0. And then, okay, let's not do this. Let's do it this way. And then the output of this. So output of this is going to be str of single neuron 1,0, the first one. Right. So the output is 1, right? So for 1,0, the output is 1, essentially, with a bias of with the given weights and the given output. So let's do this for 1,0, for 1,1. No, let's do it this way. Let's do it normally. So 0,0, 0,1, 1,1, right? So that's the regular way of doing it. So let's do 0,0, 0,1, 1,1. 0, 0, 1, 1, right? So that's pretty much it. So this is a single neuron, right? This doesn't do much, right? It's a single neuron where an input of 0 gives you an output of 0, but if any of the inputs are high, then it gives you a high output. So what does this remind you of? Okay, so we have created essentially an OR gate. The very simple OR gate. That's all we have done. Um, where low produces low, or if a single output is high, it produces high. Oh, for an OR gate, there would also be a 1,0, right? So there would also be a 1,0, 1,0, and a 1 and a 0. As you can see, this is essentially an OR gate, right? So let's start making it more complicated. So let's put in an activation function, right? So with the so why do we need activation functions? Well, we talked about this yesterday, right? So the job of an activation function is to introduce nonlinearity, right? So if you don't have activation functions, then your outputs are going to be strictly in the linear realm, right? And without an activation function, well, you can't really learn any complicated decision boundaries, right? You are always limited to linear boundaries like this, right? And to get a complicated decision boundary like this, um, like you can see the shape, you need to introduce some nonlinearity uh, within uh, within your activation function, right? Because otherwise, if no matter how many you are stacking, you're never getting a nonlinear result, right? Because all your input calculations are strictly linear. So we talked about. So what are the ones that we talked about, right? We talked about uh, sigmoid, tanh, linear. So let's create all of them, right? So let's create sigmoid, which has an input Z. Um, this is very simple, right? So we saw the sigmoid activation function here. This is the sigmoid activation function, and this is the derivative of the sigmoid activation function. So we can calculate both of them. So the sigmoid activation function is 1 over, sorry, 1 plus e to the power of minus z. So because we're using numpy, we can just do numpy.exp minus z. Right. So that's pretty much it. So that's the sigmoid function. Since you have created the sigmoid function, let's do the sigmoid derivative as well. So right, sigmoid derivative, right? Because it's very similar, right? So for the sigmoid derivative, we saw that it was if g of x is the sigmoid, then the derivative of this function that you see here is g of x times 1 minus g of x, right? You know this is very simple differentiation. So we calculate the sigmoid first. So sigmoid of z, and then you return s times 1 minus s. That's it. We also have, what are the others? We have uh, the clamp function is very simple, right? So this is a one line, uh, like the sign of the clamp function is very simple, right? So like there's no need to create a separate function for it. We can do tan h, which is again very simple, which is just np dot tan h. So there's no need to do that either. Um, like just doing np dot tan h would do the tan h function. Let's do ReLU, right? Rectified linear unit. So this is essentially figuring out the what is higher. Is it like if it is you shift the value up, right? So you pick the whether if the value is negative, you shift it to 0, and if the value is positive, you leave it as it is. That's what ReLU is. So it's very simple. So for ReLU, what you do is you return whichever is higher. You return if 0 is higher, then you return 0, or if z is higher, you return z. So it's just np dot maximum between 0 and z. That's the rectified linear unit. Maybe we do the others as well, just to round it out. So sine of z would be return 1 if so it's this thing, right? We're doing this. We're just doing this. So this is sine, and then what's the other one? Tan h. So def tan h of z is return numpy dot tan h of z. Right, we're done. So one way to check this is print out all the values. Right? So let's say you have a bunch of different values, right? So you print out. Uh, let's take a look at what this looks like, right? So let's go from -5 to +5, and what it looks like for each of these right? So let's say for the z val in -5, -3, -1, 0, 1, 3, 5. Yeah, it's fine. You print out all of them. Right? So you print sigmoid, uh, plus so this would be str of sigmoid of z underscore val. Right? Plus this. So let's copy this out a little bit so that how many do we have? We have 1, 2, 3, 4. So 1, 2, 3, 4. So sigmoid rectified linear unit would be ReLU. Then we have sine would be sine. Then tan h would be would be 10H. And let's put a new line at the end. Okay. Why do I feel like I have missed out on a bracket somewhere? Oh yeah, I have missed out on a bunch of different brackets. So there'll be a bracket here, a bracket here, and a bracket here, a bracket here, and this. Okay. Aha. It should be like this. All the plus signs were inside the quotation marks. Oops. Okay. And well, I should have clamped them to like a few characters, but you can see this, right? So it goes from -5 to +5, right? So for -5, the sigmoid value is essentially 0.007. ReLU is 0, sine is 0, tan H is -1, right? If you round this off, this is -1. And you can see the sigmoid function goes from almost 0 to almost 1, right? So you have essentially clamped the value, right? So this, if you remember this sign, so this is what we have done. We have taken the set of values and we have clamped them to this direction. And that's what tan H does as well. That's what sine does as well, right? So you can see that sine is 0, 0, 0, 0, but then at the exact value of 0, it jumps to 1, right? So remember that because of this discontinuity, right? Because of this discontinuity at the point of 0, the sine function is not differentiable. That's what so you cannot use gradient descent for your backtracking, right? It's going to fail if you're using the sine function because it requires you to do this. Someone has a question? What's up?
Professor, I cannot find where the ReLU was. Can you show me again the block that is has the ReLU? Oh,
Yes, here.
yes, thank you, Professor. I was missing that during the
All
code
right,
chat.
fine. No. So let's move on, right? Okay, so this is why we are going to essentially going to use sigmoid, right? Because of how smooth sigmoid is, it is constantly positive. It's always between 0 and 1. And it's a very simple thing, but the derivative is very easily calculated, right? And it's a classic for a very good reason, right? So let's build this network, right? So let's build this network and train these parameters, right? With the given biases. So let's build this, right? With one input layer, with one input layer, one hidden layer, and one output, right? This is not going to be very powerful, and you're going to see that it's not powerful at all. So the first thing we want to do is we want to create the input and the output, right? And uh, this is critical. I mean, I'm not going to teach you programming, but make sure that the shapes are correct, right? So the inputs are the x values, right? So the input is a 4 by 2 matrix essentially. So let's create numpy dot array. Let's not create like a direct matrix. So this is the easier way to do it. So you have the first, it's 0, 0, 0, 1, 1, 0, 1, 1, as we saw in the previous. So it's 0, comma 0, uh, uh, 0, comma 1. Why is the, aha, I put in a Yes. 0, 1. 1, 0. And 1, 1. And we will expand this later, right? To maybe 3 digits to see if we have enough. So this is a 4x2 matrix, right? And we are doing a XOR gate, right? So we need an output as well. So the output is going to be another numpy.array, but instead of a 4x2 matrix, it's going to be a 4x1 matrix. So, and you can extend this later. In fact, I may even have like an in-class assignment where you add in one extra hidden layer. So for an XOR, 0, 0 XOR is 0. Right? And 0, 1 is a 1. 1, 0 is a 1. And 1, 1 is a 0. So that's that's our values. So we could print it. Let's print it. Just so that if you change this, you can see what we are doing, right? So for I in range, let's not do 4. Let's do, if we extend x, so we might require more. So let's make it length of x. Let's print. Let's do f strings. Okay, I'm pretty bad at f strings, so if I mess up something, let me know. So we want to print x I 0, so it should be x I comma 0. Let's do 4 spaces. Yeah, 4. We should put it in. We're doing f strings, so we need to put it like this. So then let's do x I comma 1. And similarly, let's do 4. And let's print y. And y is 4x1, so it'll be just I 0. I comma 0. Four. So this is our values, right? Actually, let's do let's print just x. I don't know. The input one, right? So I1, or no, we are calling it x. So let's do x1, x2, and the output is target. Yeah. So let's just call it what. Yeah. So if we increase this to like 3 bits from 2 bits, you can just expand this and it'll make it easier to see, right? So we are no longer going to do a single neuron, right? So let's figure out how do we assign the weights, right? So initially, generally speaking, most of the time the weights are assigned randomly, right? So you take any value between like say I don't know, +5 and -5, and then you assign values to it, right? So let's do that here as well. So let's do a bunch of initial random initialized weights before we calculate the forward pass, right? So we need to do, okay, what is the structure of a random again? Let me print it once before. So apply.random.rand 10. And this has to be a 2 by 2. So what does this look like again? Okay, yeah, that's what I want. So I want random values that are like this. So so instead of doing 3 by 3, yeah, okay. I was wondering if it would be okay. So the weights are going to be W1 is the first weight that we are going to assign, is going to be a 2 by 2. No, these are too high, so it should be 1 by 1. No, no, I've just multiplied it by 0.5. I've just divided by 2. Yeah. This is much better. And the threshold, T1, is going to be whatever. Again, let's randomly assign the threshold because we don't know. These have to be learned by us. So let's pick a value between 1 and 2. And do this one more time. So W2 and threshold 2. Right. So we have all of these randomly assigned weights and values. Right. So let's do the forward pass. Right. So which we have seen, which we have calculated here. So let's do this particular forward pass. Right. And without like we don't really need a learning rate here because we're not really learning anything. So let's do a very basic forward pass and see what we get. So let's define a forward pass. So what do we need? We need the input. So the input, did I call it x1? No, we call it x. So the input is x. We need weight 1, then threshold 1, weight 2, then threshold 2, and that's it. Right? We are going to need stuff more. We are going to need more things than this, but we'll do that later. All the backpropagation stuff we're going to do later. So we're going to need to do a little bit of matrix math, right? Because Z1, which is the output of this, is a multiplication of this and this. So like two weights are being multiplied with this value, right? So fortunately for us, in NumPy, you can do matrix math, and NumPy has a special operator that does matrix math, right? Now, what you have to be careful is, are your indices matching, right? Remember back to your high school matrix math calculator, right? So you need to multiply the input, which is x, right, with weight 1. Now, what is the dimension of x? X is 4 by 2. And what is the dimension of weight 1? It's 2 by 2. So what is your output? It is 4 by 2, right? And you add in the threshold to this. So it should work, right? So let's do Z1, Z1, or if there's any American in this class, it would be X. And we're doing, remember, this is, you can't do a star. We're doing matrix math. So it has to be an at. So this is the matrix math operator for NumPy, right? So W1 plus the threshold, right? And then, well, we already have Z1. So what to call it? Activation. So let's call it, I don't know, A1 is the sigmoid of Z1, right? And then we do this for Z2 as well. So we for Z2 we take this output, right? So A1 gets multiplied by W2, and the bias is threshold 2, and then A2 is the sigmoid of Z2. That's pretty much it, right? And you return these. Right? So you return all 4 of these. So
You need to unlock your iPhone first.
some reason Siri thought that I was talking to her. Whatever. So you return Z1, A1, Z2, A2. I don't think there's any error. Okay. So let's run it once, right? Let's do let's not write all of this out again. So this is equal to forward pass as whatever. Okay, we call it x comma w1 comma d1 comma w2 comma d2. That's it. So what is our original prediction? So we need to print both the prediction and what we got, right? Before training and after training. So print predictions as how do we get our predictions? So um, it is A2, right? A2 is our prediction. So um, and after multiplication, it's going to be 2, 1. So we need to flatten it. So let's do str A2 dot flatten, I think. And we're going to get like a huge value. So let's not make the same mistake that we did here. And let's just round it to like 2 digits. So that's, or maybe 3, like round it to 3 digits. And yeah, we need, what was the target as well? So the targets were this remains a string. It's just going to be y dot flatten. So let's see what it looks like. Okay. It's pretty bad. Right. It's not good at all. I mean, the network hasn't really learned anything yet. So I hope these were correct. Like so Z1, A1, Z2, A2, forward pass X, W1, T1, W2, T2. Right. Yeah, no, this looks perfectly correct. Correct. So wait, the threshold. Oh, this is wrong. Yeah, the second weight cannot be 2, 2. It should be 2, 1. Right. Okay, this makes, yeah, because that's why we have so many values. Yeah. Okay, this is much better. I was like, I didn't want to say anything. I was like, why do I have so many values? Okay, so now we have 4 values. So they are completely inaccurate. We're supposed to get 0, 1, 1, 0. We are getting this, right? And even if you round it off, the accuracy is just going to be like random accuracy. We have not really done anything to improve the accuracy, right? So what is the first thing we need right now is we need to figure out how far away are we, how far are our predictions from our target. So we need to find out the loss function. So what is the standard loss function that we all know well? There are 2 like common loss functions, right? Which is sum of squared of error or mean squared error, right? MSE or SSE. Or we can just simply subtract. So let's write mean square error because that's very common. Oops, where did I go? Okay. So let's write mean square error loss. Okay, no, don't call it loss because loss is a library function. It's very often a library function, so you are going to have namespace problems. So let's call it loss computation, compute loss. Let's call it compute loss. What do you need? Well, you need the original targets, and you need our predictions, right? You need A2. A2. To calculate the loss, we need something in the shape of Y. So we need a 0. So okay, so Y dot shape 0, I think is this right? Let me yes. That is going to give me the instead of len, this is going to give me the correct. Right. So loss is going to be it's a mean square error, right? So it's going to be np dot sum of the difference between y and a2, right? So it's going to be y minus a2 squared. So we can do np dot no exponent. No, let's just like that. Right. Oh, multiplied by 1 over n. Right. So that's the loss, and you return the loss. I think that's it. So what's our current loss now? So print current loss. This is pre-training, right? So let's put it in brackets that this is pre-training. We ran one forward pass. We haven't trained anything. So it's going to be str of compute loss of y comma a2. Supposed to be a plus. Okay, so our loss is roughly 25%. Right? That's pretty high. But if we think of loss this way, right, that this is different from prediction, right? If you were doing prediction, like if you're doing accuracy versus loss, then that would be much higher, right? So that would definitely be much higher. And just to be sure this is correct, let's calculate the perfect prediction as well. So that would be an np dot array of that is essentially going to be y, right? So it's going to be this. So this is let's pull it in one line. Let's not mess around with the. So this is our perfect predictions. Okay. So if the predictions were perfect, what would we get, right? So perfect loss with perfect prediction would be compute loss instead of YA2 would be perfect. Oh, sorry, it's my bad. It's perfect prediction. Yeah, so it's 0. And something else you should keep in mind is what if instead of being a perfect prediction, what if our predictions were completely random, right? So if our predictions are completely random, all of them would be 0.5. Right? Bayesian random, not in technically a complete random result can also this can also be a completely random result. So that's not what we care about. So we want something like 0.5, right? So what happens if our predictions are equally far from both results. Like 0.5 is equally far from 0 and from 1 at all stages. So what does the maximum loss look like? Right. So essentially maximum loss. So in that case, it would all be 0.5. So we just make a copy of y, but we fill it up with 0.5 values. So numpy has a function for that. So now that is numpy dot full like, and what that does is it creates a copy of the same structure as y, same shape as y, but it fills it with the value that we give it. And the maximum loss you get here is 0.5. That's for your understanding. So now that we know this, what is the next step? Well, the next step is backpropagation. So, and I'm not going to go into full detail of how backpropagation works, right? But the backpropagation is essentially the chain rule, right? We're applying the chain rule of calculus, but we're applying it back to back to back, right? We're stepping back. We know the value here, right? We know the output here. We know the loss here. So we know that this is a forward path calculated from A3 and A4. So we calculate the reverse derivative, so like of the activation functions, and we recalculate A3, A4, X1, X2, and we re-update the weights. I mean, we update the weights and then we recalculate these values. So let's do backpropagation. Right. So we are doing chain layer for our very simple two-layer network. Right? So we are doing backpropagation for this. So what do we need? Right. That's for backpropagation. We need a few more values. Right. So we call it forward pass. So let's call this backward pass. Right. So we need the target because we need to calculate loss. Right. And we need the input. So we need both the input and the target. Right. And we need all the layer definitions, right? Z1, A1, Z2, A2, weight 1, the bias, first bias, weight 2, and the second bias, I think that's it. W1, T1, W2, T2. Oh, we need gamma, right? We need a learning rate. So we need gamma. Okay. So okay, so let's remember the learning rate specifies like how big of the steps are we taking when we are like moving backwards, right? So that's very important. So the first thing we're going to need is the shape, like how long this is. So x dot shape 0. Okay, so now we need we need to do we are doing gradient descent, right? So we need to calculate the gradient descent for the final layer, right? So we are doing essentially a DDX of A2. So we're going to do we are integrating with we are differentiating with respect to A2. So it's not DDX of A2, it's D of the output layer, DO or DL over A2. So let's say it's DL underscore DA2. I think that's understandable, reasonable. Okay. So that's what is the value of this again? Okay, so it's going to be this is the derivative of the loss. So it is I'm trying to do it in my head. We did mean square error, so it's the derivative of this. Okay, so the mean square derivative of this is going to be it's minus what? Minus 2 over n. Okay, it's minus 2 over n. Someone check my differentiation. Y minus 8. Yeah. Okay. So this is like the output layer. So this is this here. We are doing the reversed differentiation. So we need to go one step back for both of them. Right. So we need to compute DL underscore Z2 as well. Right. So Z2, which is this is much simpler. Right. So this is just this times the activation function differentiation. And our activation function was sigmoid. Activation function is sigmoid. And I think we already calculated the sigmoid derivative. Yes. So it's going to be the sigmoid derivative of Z2. Now we need to calculate weight 2. So like this weight. So that's going to be DL DW2. Yes. And that's going to be this. It's going to be the sigmoid of Z1 multiplied by DLZ2. It's going to be Z1 at DL underscore DZ. Is this correct? What is the structure of A1? A1 is going to be 4, 2. No, it needs to be 2, 4. So we need to transpose this. No, we need to transpose A1. Yeah. And then finally we have the threshold, right? So D2, which is going to be simply the thresholds are very simple, right? They're scalar values. So you just add them up. You essentially flatten them and then you add them up. So and we don't need to flatten them because np.sum is going to do that for us. So so it's going to be DL dz2 over which axis? Over axis 0. Okay. 0. You don't need to keep dims. No, you do need to keep dims. Okay. That's it, right? Those are all the gradients for the output layer. And now we need to do this for the hidden layer as well. Very similar. Only the advantage is that for the hidden layer, so these were for the output layers. For the output layer gradients. Now we need to do this for the hidden layer gradients. One advantage, slight advantage for the hidden layer gradients is that we don't have to deal with mean square error. So this we don't have to do this weird differentiation again. So all we need to do is, and this is very simple, right? We are coming to the A1s, right? So it's going to be DL underscore DA1, and that is hang on. I have confused myself. So I think it's going to be Z2. DL underscore T Z2. Matrix multiplication with the weight 2. And transpose of the weight 2. Because it's 4 2, it's not 2 4. So we need to do that. Then DL dz1 is going to be the same as this, because again, this is symmetric. So it's going to be the same as this. It's just we need to change the number. So instead of Z2, it's going to be Z1, and all of these are going to be ones. Right. And the same here. Right. So it's going to be DL dw1, and instead of A1, right? Instead of A1, we are going back here. So we are hitting X1. Right. So it's going to be, I mean, there's no X1, there's only X. Right. So both of them are dashed together. So DL dz1. And this as well, it's the exact same thing. So DL dt1 is going to be the sum of DL dz1. Okay. So I think this is correct. Well, we are going to find out, right? So now we need to do the weight updates, right? So we have W1, we have threshold 1, we have W2, and we have threshold 2, right? Now what we need to do is use gamma to do our weight updates. Right? So we need to do this part. Right? Yeah, we need to do this part. Right? So we are updating W1 because we have already computed this part, right? So we are updating W1. So this is equal to this minus this, right? So this is going to look slightly different because we have pre-computed a bunch of things that were not computed over there. So we are going to need to multiply the differentiation like DL dw1 with gamma. But if we are doing that, then we can't add it. We have to subtract it from the old weight. Right? So it's going to be W1 minus equals gamma times DL underscore dw1. No, it's not this, it's minus equals. And same for W2, dw2. And we need to do it for the threshold as well. Right? So T1 is gamma times DL dt1, I think that's what we called it. And then threshold 2 is DL dt2. Right. And we do this as many times as needed. Right. So what are the parameters we have trained? Well, we have trained W1, W2, and threshold 1, threshold 2. So return all of them. Right. And remember the order, because that is going to mess us up if we're not very careful. So P1, W2, T2. Okay. I'm sure I've messed something up, and the results are going to be completely calamitously bad, but let's see. If anyone is already on Teams, check to see if your in class is up.
Yes, sir. The assignment was up, sir.
Yeah. Okay. Okay. If it's up, you can continue to watch this because I don't think the assignment is going to take you very long. It's going to take you like 5 minutes. Right. So just take a look at the assignment if all of you want, and then you can continue on. Am I still cutting off for people? Eric said that I was cutting off, right? Okay. Oh, and we are computing the loss for for the final output, right? We don't really need to compute the loss for A1 because that makes no sense. That's the output of the hidden layer. Okay. So let's do the same thing that we did for our forward pass, right? Let's do this exact same thing all over again, but with like a lot more values. Right? So let's do let's copy and paste this again. So Z1, A1, Z2, A2, instead of forward pass, it's going to be backward pass. And so backward pass. And we're sending it a bunch of values, right? So we're what we need to send it? We need to send it X, Y. Sending it X, comma, Y, comma, Z1, A1, Z2, A2, and then W1, T1, W2, T2, and gamma. So let's give a gamma of like 0.5. And then no, this is let's move this. So let's do the backward pass, then let's do the forward pass with the let's do the forward pass again with what we have now with our updated weights, right? Wait, this is not it. It's going to be W1, sorry. Yeah, we are returning W1, T1, W2, T2. So return the backward pass gives us this, and then we put this into the forward pass, right? So let's see what the new loss is. So we need to compute loss again. So post back propagation loss is equal to compute loss. Wait, did we compute the loss before? Okay, you know what we should have done? We should have computed the loss here. So let's just so that we could so let's call it pre-BP loss is equal to compute loss. I'm doing all of this, but without. So let's start from here, just in case I have changed something. Let's do this again. Do this again. Compute loss would be the same. This should be the exact same. Backward pass is correct. So we have pre-BP loss and post-BP loss. So compute loss by A2. So let's print both of them. So let's do this. How will we print losses again? Okay. Pre-BP loss is STR of pre-BP loss. And let's see if I've messed up somewhere. Oh no, we haven't. Should be post. it went down. The loss went down very slightly. Right, it went from 25055 to 250377. Right, if we do this multiple times, you can see that it is going down because we are constantly, every time we do this, we are doing one more round of backpropagation. So you can see that this value keeps going down. Eventually, we are going to maybe someday, if we keep running this 25 million times, we are going to go beyond, go below 0.25. Right. So maybe if we change the gamma to from 0.5 to 0.9, yeah, it's going down slightly faster. And now you can see that it has gone to 0.2499, right, from our original 0.25055. Right? So this is terrible, but we have done something, right? We have managed to do a little bit of improvement using our few backward passes. So so let's do this again. Let's do this like, I don't know, 100,000 times. Maybe. So what we should do is we should reinitialize everything. Right. So let's copy and paste this again. And let's give it a seed this time so that you can pick a value. Right. Let's again pick a completely random value that has no meaning whatsoever. And then let's say, so one pass, like one complete pass, is called through the entire training data. And our training data is very small, so it doesn't matter. So one pass is called one epoch. Right. So let's say we do again 100,000 epochs. I mean, it's not going to matter. Our system is too simple for it to improve much. So even if we do, instead of 100,000, even if we do 500, we're not going to see much difference, right? But still, let's see. Right? So our learning rate, which is our gamma, is I don't know, 0.5 is like way too high. So let's give 0.3, right? So we have two hidden units. We are doing simple gradient descent. That's pretty much it, right? So let's set this, and then let's do a full training run, right? So for epoch in range, we start with 1. Don't do a 0, right? So epochs plus 1. Okay. So let's copy and paste this. Z1, A1, Z2, A2 is a forward pass of X, W1, T threshold 1, W2 threshold 2. Right? So this is the first thing we do. Then we compute loss. Actually, let's have a variable that that tracks the loss. Right. So we can see how our loss is improving, because that's something all machine learning libraries do. So let's have a simple list like loss history, which is going to be an empty list. So a very simple loss history list, right? So we compute loss, then loss history dot append loss, right? And then we do this bit, we do the backward pass, right? So we have weight 1, threshold 1. Actually, this is kind of hard to see. So let's drop this. Yeah. weight 1, threshold 1, weight 2, threshold 2, X, Y, Z1, A1, Z2, A2, W1, threshold 1, W2. And gamma in this case is going to be, what did we call it? We call it learning rate. So 0.9, let's call it learning rate. And yeah, that's pretty much it. At a few, so let's see what the loss and the predictions are at different points. So let's print them. So if epoch is in okay, for 100,000, what 1, then 10, then 50, then 100, 500, 1,000, 5,000, 25,000, 50,000, 100,000. So what we want to see is the prediction. So Preds is the predictions are A2. Remember, this is the final output of our final list. So A2, and we need to flatten it and then round it to like 3 digits, and then we print it. Print do an F string. Nah, I hate F strings. So let's do so epoch is plus str of epoch plus loss is plus str of loss plus predictions is plus str of Reds. What else should we do? Well, we could check how long it took. Right, that's something we can check. How does one check how long it takes? Well, we could put in a timer function. I'll think of the timer function later. So we'll do that later. Right. So let's print our predictions versus our targets, right, and our accuracy and our loss history and all of that, right? So let's see. Oh, we never. Oh, this is not epochs. This is epoch. Oops. We never. Sorry. Wait. Is it not round?
In the function of the flatten, sir, I think you missed the
Oh.
right in the flatten.
Oh. It's a yeah. You're right. Thank you. Okay. Oh, the loss goes down a lot. Right. Hey, it's pretty good. We have pretty good loss. So our predictions are 0, 0.9, 0.9, 0.011. That's pretty good, I'd say. Right. So let's let's print all of them. Right. So let's do for I in range. Thank you for pointing that out, because it would have taken me forever to remember that I didn't put my brackets in. So for all 4 of them, so the predictions are A2, right? So A2, I comma 0. The targets are from Y. So it's going to be yi comma 0. Oops, extra brackets not needed. Let's round them values, right? So um, rounded is we round the values of predictions, right? So if it is 0.012, it should be 0. And if it is 0.986, it should be 1. So that's what we want, right? So it should be round of prediction, right? And then we want to see the accuracy, right? So we want to see the correctness. So let's call it correctness is what? True if rounded is equal to the target, else false. So this is going to check whether our things are correct or not. Right? So let's print them out. There's a lot of things to print. Actually, we did this, right? We did this somewhere over here. So I don't want to do this again, so let me copy and paste this. Oh, I should copy and paste both of these things. So let's copy and paste x1, x2. Oops, sorry. What are we need? We need to print x1, we need to print x2. So that would be, we need to print the target. We need to print, what else are we printing? Oh, we need to print our predictions, right? So what do we call it? Predictions. Yeah. And then correctness. That should be enough. I mean, there's probably more values we could print, but I don't care. We're running out of time. So let's print all of these. So, okay, 10 is x1. No, it's not 10. I0 is x1, I1 is x2, yi0 is the prediction. Okay. What else? Next is no, it's not. It shouldn't be yi0. It should be. I already have it here, so let's just call it target. So the next should be prediction. So we call it red 4. Then rounded and then correct. Rounded and then correct. Are these all 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5. Wait, no. Whatever, doesn't matter. We're doing it. Prediction, rounded. This is this is this. This is the target. This is the predictions. Let's just put in rounded. Binary. So instead of rounded, let's call it binary. So what mistake did I make? Oh, it's 8. Sorry. Okay, so instead of 4, let's make this, I don't know, 10, 12, 12, 12, 12, 12. And let's the prediction, let's round it to like I don't know, 10. So predictions is too much, so let's make this 8. But 10. Whatever, you get it, right? So the binary value is 0, 1, 1, 0. So our goal has been achieved, right? So what is our, let's calculate our final accuracy. So accuracy is, so A2 minus, if A2 is equal to Y, right? So NP dot mean, I mean, it's going to be 100% because we were correct, but we dot round A2 equal to Y times 100, and our final loss at the end was loss history, the last one. So we are doing a little bit of manipulation, so it's -1, right? And we print both of these. So no need to do all of this. So let's do print. And then print again. So accuracy plus str, close, bracket open, quotations, colon space, plus str of this. Right. We have 100% accuracy and our final loss is 0.001. Right. You could visualize this. So what this means is that this huge thing that we have created, eventually somewhere between the epochs of 5,000 and 25,000, you can see that the loss went, it suddenly fell, right? That somewhere our somewhere within our churn, it suddenly fell, and we got very close to the actual values, right? It went low and it stayed low after somewhere between 5,000 and 25,000 epochs. So we came up with something. So what you can do is come up with like more complicated equations, like more complicated binary expressions that you think that you want to test it out with. So and or are going to be very simple, right? You can run it very easily and you can get good results. XOR is more challenging, and we can see that our original, what we have originally predicted, that a two-layer perceptron can approximate any function is true, right? But we are going to need nonlinear. We need to introduce nonlinearity. We introduce nonlinearity uh, through the sigmoid activation function, and that essentially gave us good results, right? And that's why you can see that eventually we managed to get like pretty good results, and our training was successful, and we did manage to predict things very, very well. So let's scroll. This is why I don't like F strings. It's so okay. Yeah, this is much better. It looks way better. Okay, I will share this lab with you. I know many of you must have had questions. Oh, how long should you wait with the EPUB before taking a screenshot? Well, it's up to you. When you see that things have gotten stable, that's when you stop. Right. Sorry for not spotting. Yeah. Okay, you should keep working on your in-class assignment for today. It's very simple. It's not going to take you more than 5 minutes. So yeah, just keep working on it. Submit it. Please submit before 6 o'clock. Don't send me an email 30 minutes later saying that you were working on it and you forgot to submit. Please submit before 6 o'clock. It's a very simple in-class assignment. Right? And I'm going to share this file with you as well. Oh yeah, you can have more than one intermediate screenshot. Yes, it helps us as well, right? We get to see what you are doing. I will share
Okay, so
this,
just to
and
make sure you want 2 screenshots minimum, right?
yes, 2, just so that we can compare, right? Yeah, 2 screenshots minimum.
Okay.
But you can submit more, of course. We are going to build on this, like this neural network that we have created here is very, very simple, right? But we are going to build on this. We are going to add in regularization. We're going to add in more activation functions, and slowly as we learn, you are going to see what makes neural networks so powerful, right? Even this extremely simple neural network that we created, like this very simple neural network that we created, already managed to approximate the XOR function, right? And so you can imagine as you add in more neurons, as you make it more powerful, why it's called a universal approximator, right? Why the theorem, the universal approximation theorem caught on, because of if you have a 3-layer neural network, you can literally approximate any function. As long as you can represent your problem as a function, you can approximate it as any function. So it's a very, very powerful learner, right? All right, so thank you. Yeah, sure. You can send those screenshots, Jay. Yeah, that's no problem at all. All right, I am going to stop the recording now.